In section 8.7, we're going to be working with special factoring patterns, and we want to do that so that we can factor using those special patterns. Earlier in this chapter, we learned how to multiply using those special patterns, and the key vocabulary here is what is a perfect square trinomial. So let's talk about that a little bit. The first thing we want to do is look at the difference of two squares. So we already learned that if I have conjugates, a plus b and a minus b are what are called conjugates. And they're called conjugates because the only difference between the two binomials are the signs. You'll notice that a is a and b is b, but what's different are the signs in those binomials, and this is what makes them what we call conjugates. And conjugates create the difference of two squares. And that happens because you'll have a positive AB and a negative AB that will always combine to eliminate each other. So the middle terms, the outsides and insides, combine to make 0. Okay, so what we want to find here is identifying, well, what got squared? What got squared to make 49? Well, 49 is 7 squared. And what got squared to make 121p squared? Well, that would be 11p. So now I know what a and b are. I know I've got 7 minus 11p times 7 plus 11p. And this way I can factor it by recognizing the situation and then following this special pattern. Okay, if we look at this one, 225 was x squared is what? Well, it's 15x squared. And what makes 144y squared? Well, that's 12y squared. And I can go ahead and then write out the conjugates once I know what a and b are. Okay, so identifying special patterns involves looking at, is that a perfect square? Yes, that was 7 squared. Is this a perfect square? Yes, it's 11p squared. And then we know we're in the difference of two squares. Okay, these are perfect square trinomials, right? And this is the form a squared plus 2ab plus b squared. And when b is negative, the only thing that changes is this sign. Everything else will stay the same. Okay, so again, what we're going to want to do is we're going to want to identify the pattern. We're going to want to know, is this thing a perfect square? Is this a perfect square? And is this middle term 2 times a times b? So for example, is x squared a perfect square? Yeah, it's x squared, so that would be the a. And is this a perfect square? Yeah, 9's a perfect square, it's 3 squared. And now I want to look at this term, and is it 2 times x times 3? Well, it's 6x. Yes, it is. Okay, so that means this is the square of x. This is what the parts we'll use, x plus 3. Okay, and when, like I said, when this is a minus sign, the only thing that happens that's different then is that this becomes a minus sign. Okay, so let's do one of these. If we take a look at this, is this item here in the front, is the first term here a perfect square? Yeah, this is 7a squared. Is 1 a perfect square? Oh, absolutely, it's 1 squared. And is this middle term, is it 2 times 7a times 1? That would be 14a. Yes, it is. That checks out. So I know that this is 7a, right? So again, the parts I'm using, I'm going to use 7a plus 1. Plus 1 squared. Let's take a look at another one. So if we look at this one, is 2x squared a perfect square? No, it's not. It's not, but if I look at this more closely, I'll see, oh, well, I could factor a 2 out of all of this. And once I do that, is x squared a perfect square? Yes, it is. It's x squared. Is 9y squared a perfect square? Yes, it is. It's 3y squared. Is this middle term 2 times x times 3y? Well, this would become 6xy. Yes, it is. That checks out. So again, this is going to be x plus 3y squared. If you're unsure whether you've done this correctly, you can always multiply it out, and it should go back to being the original item. Remember the 2 had to continue to come down. It's always part of the factoring. All right, let's take a look at another problem. A couple different ways I might want to address this. First off, I don't really want to work with a negative leading coefficient. So what I can do is just add everything to the other side. Okay, equally, I could have just multiplied both sides of the equation by -1. I'll get the same thing. If I look at this, these are all even numbers. That means I can factor a 2 out of each of them. And then I have 2 times h squared plus 14h plus 49. Okay, so I always, when I begin a problem, want to look to see, is there a monomial factor that I can take out of all the terms? And in this case, there was. I could take out 2. Now, when I look at this, is this a perfect square? Yes, it is. It's h squared. And is this a perfect square? Yes, it is. It's 7 squared. And is this middle term 2 times h times 7? That would be 14h. Yes, it is. So this is h plus 7 squared. Okay, now if I want to solve this, notice the key difference here is they asked me to solve it. I want to find the values of h that will make this equal 0. Well, 2's never going to equal 0, so it's not part of this. But h plus 7, if I set that to be equal to 0, h will be equal to -7. And that's my solution. Now, polynomials always have as many solutions as the degree, so I know this has 2 solutions. But remember, the factors were both the same. The factors are both h plus 7. So the solution is -7, and this is a repeated solution. So -7 is a solution 2 times. Okay, we don't normally bother writing -7 and -7. That's redundant. But it's good to know it's a repeated solution. Okay, because sometimes when we work with larger polynomials, we want to keep track of whether or not we found all of the solutions, right? I found -7 2 times, so I have found all of the solutions. A final example here, when we're looking at a falling object, a window washer drops a wet sponge from a height of 64 feet. After how many seconds does the sponge land on the ground? Well, when it lands on the ground, remember we're going to work that the height will be equal to the effects of gravity, which is -16t squared, plus initial velocity, that's velocity at time 0 times time, plus the initial height. Okay, he drops the wet sponge. That means that v sub 0 is 0. It has no speed, no initial velocity when he lets go of it and drops it. He's starting at a height of 64 feet. Gravity's still gravity. And we want to know after how many seconds does it land on the ground, right? On the ground means it's at height 0. So when I simplify this, I'll get -16t squared plus 64. All right, and if I want to solve this, remember I don't like those negative leading coefficients. I'm going to multiply everything by -1. Equally, I could add 16t squared and subtract 64. The effect will be the same. And now when I look at this, I go, oh, well, is this a perfect square? In fact, actually, I would also look and say, well, I can factor a 4 out of all of this, right? If I factor out the monomial, this will be 4t squared, and this will be 16. Oops, I can actually factor a 16 out of everything, right? So when I do that, I'll have 16 times t squared minus 4. Now this is t squared a perfect square? Yes. Is 4 a perfect square? Yes, it's the square of 2. So that means I've got conjugates, t plus 2 times t minus 2. So if I want my solutions, t is going to be equal to negative 2 and t will be equal to 2. Well, let's think about this. After how many seconds does the sponge land on the ground? Could it land negative 2 seconds after I drop it? No, that's in the past. This has to be the solution. It's going to take 2 seconds to hit the ground. Okay, and that's working with special patterns.